There are two questions given here, but in the exam I can choose either question A or question B. First, let us find the answer for question A. Here the questions derive the expression for the torque acting on an electric dipole when it is held in the uniform electric field, and identify the orientation of the dipole in the electric field in which it attains a stable equilibrium. First, let us consider the uniform electric field. In this, we have an electric dipole consisting of charges plus Q and minus Q. So we'll take point A and B here. So then whose length is, the dipole length is 2A, is placed in uniform electric field of E, which make an angle theta with the electric field. Now we have minus QE here and plus QE here. Now let us take this point as N. Now we'll write force on charge minus Q at point A, which is equal to minus QE, opposite to E. Now force which act on charge plus Q at point B, which is equal to QE, along the direction of E. So the electric dipole is under the action of two equal and unlike parallel forces, so which give rise to a torque on the dipole. So therefore, torque can be written as force into perpendicular distance between two forces. So we can write torque equal to QE, the force, into perpendicular distance between two forces as AN. So this is the perpendicular distance. So AN. Now we can write T equal to Q into the perpendicular line. AN is nothing but 2A sine theta. Now T equal to Q into 2A times of A into sine theta. So we can write T equal to PE sine theta. So finally we have torque equal to P cross E. So from this we can say that in a uniform electric field, the net force on dipole will always be 0, but torque is 0 for theta equal to 0 degree and theta equal to 180 degree. Now let us solve second question B. Here the question is obtain the expression for the energy stored in a capacitor connected across a DC battery. Hence define energy density of the capacitor. So here the energy of the charged capacitor is measured by the total work done. The total work done in charging the capacitor to a given potential. Now we are going to assume at any instant a charge Q be on the plate of a capacitor. Then potential difference between the plates is written as V equal to Q by C. We know that Q is the total quantity of charge transferred. When additionally small charge dQ is transferred from the negative plate to the positive plate, the small work done is, we can write it as dW, which is equal to V into dQ. So which is equal to Q by C into dQ. So the total work done in transferring charge is given by W equal to integration of the limit 0 to Q by C into dQ. So if we take C outside, we have 0 to Q into dQ. So we have 1 by C into, if we integrate, we get Q square by 2 and the limits from 0 to Q. So finally we have W equal to Q square by 2C. So this work done is stored as electrostatic potential energy U in the capacitor. So we can write U equal to Q square by 2C. We know that Q equal to CV. So we can write U equal to 1 by 2 into CV the whole square divided by C. And if we expand it, we get 1 by 2 into C square, V square by C. If we cancel out the C and C, we get U equal to 1 by 2 CV square. And also we can write C equal to U by V So we have U equal to 1 by 2 into Q by V into V square. We cancel out V and V, remaining we have 1 by 2 times of QV. So finally we have U equal to 1 by 2 times of QV. So this is the required expression for the energy stored in a capacitor. And one more they are asking us define energy density of the capacitor. So what is energy density of the capacitor? So which is nothing but electric energy stored per unit volume. So electric energy stored per unit volume. So electric density is defined as electric energy stored per unit volume.